Howdy, my name is Mark Holtzapple and I'm a professor of chemical engineering at Texas A&M University. What I'd like to do today is introduce you to Richard Smalley, who won the Nobel Prize in Chemistry in the year 1996 for discovering buckyballs. In this picture you can see the buckyball in the front. It looks kind of like a soccer ball and it's a form of carbon. He became very famous for this discovery and started teaching all over the world, and he introduced his top 10 human problems, which you can see here: energy, water, food, the environment, poverty, terrorism and war, disease, education, democracy, and population problem. Well, he made a bold claim. He said all of these problems can be addressed with energy that is clean, affordable, and abundant. So let's take a look at this list. Energy, of course, would be solved with energy, but water can be solved with energy because it takes energy to desalinate water. Food takes energy to grow. It takes energy to clean up the environment. And poverty, for a large degree, is a lack of energy. Terrorism and war, we have energy dollars going to regions of the world that are not friendly to the United States. In order to cure disease, it takes energy to be wealthy enough to cure disease. Education also takes wealth, which implies energy. Democracy takes a well-informed public, which means you have to have wealth and hence energy. And then the population, it turns out that the wealthier you are, the fewer people that you have, your population growth slows. So basically what he's saying is that the top 10 human problems all relate to energy. Okay, so with that as a little background, it introduces me to the title of my presentation, which is about energy. Okay, let's give a little background. Talk about population first. What I'm showing here is a graph of the human population going back to 10,000 BC. And you see at that time there were only about 4 million people on planet Earth, which is roughly the size of Houston. And it stayed around that population size for tens of thousands of years, but eventually it started picking up to the point now where we have 6.67 billion people on the planet. Well, there's some milestones along the way. In 1815, we reached the 1 billion milestone. And in 1956, we reached the 2.8 billion milestone. You might be thinking, well, what's significant about 1956? Well, that happens to be the year that I was born. And so in my lifetime, it's gone from 2.8 billion to 6.6 billion, almost a doubling or tripling. What about the rising standard of living? What I'm showing in this graph is on the y-axis is the per capita income, that is the amount of money per person in a typical country, and on the x-axis is the per capita oil consumption. So let's take a look at a particular example. We have the United States in the upper right-hand corner, and the average person in the United States consumes 25 barrels per year, and the average income per person is approaching $30,000. So what that means, a family of 5, which is my family, we consume 125 barrels of oil every year. And imagine putting those 125 barrels of oil in your garage. And that means every 3 days we take out another barrel of oil and consume it. And we're a typical American family. Now you see that the countries where they consume less oil are less wealthy. And in particular, you see China and India, which are in the bottom left-hand corner. They are rising economies. Their growth rate is on the order of 7 to 10% per year. And what they're doing is moving up that curve, trying to achieve a standard of living like we have in the United States. So that's going to greatly increase the amount of oil consumption in the world. Another issue is oil imports. This graph comes from the Department of Energy, and it shows on the left all the different forms of energy that are flowing into our economy, and on the right it shows the different ways that the energy is used in the different sectors of our economy, such as residential, commercial, industrial, and transportation. So the key ones I wanted to focus on are shown in red. Notice the petroleum imports in the bottom left-hand corner and the petroleum consumption circled in the center. And if you take the ratio of those two numbers, we find that we're importing 73% of the oil that's consumed in this country. Now what I'm showing in this graph is the historical price of oil going back to its original founding in Pennsylvania. And notice it reached about $100 a barrel in current dollars back in the early 1800s. And the price lowered so that during pretty much the entire 20th century, it was around maybe $15, $20 a barrel in constant dollars. But in the early 1970s, we had an energy crisis. It caused the oil price to kick up to about $80, $90 a barrel. And then it worked its way back down and formed somewhere around $20 to $30 a barrel as the new equilibrium price. And then just last year, it went up to $147 a barrel, which is a record. That no time in history has oil ever been as expensive as it was last summer. And currently, it's around $70 a barrel. So it's about midway between the highest price and the historical price. Okay, so we import about 20.6 million barrels per day of oil. 73% of it's imported, and the current price is about $70 a barrel. So that means we're spending a little over $1 billion a day importing oil, which means on a yearly basis it's about $384 billion. And if we compare that number to our trade deficit, which is about $361 billion per year currently, you can see that if we could solve this energy problem, we essentially would not have a trade deficit. Another important issue is peak oil. What's shown in this graph, where the star is located, is the expected peak in oil production. And you see it's pretty much around now. Some projections are 2005, some say 2010, but we are soon or already on the decline side of the production curve of oil. We also have this issue of global warming, which is very controversial, I understand that, but there's a lot of evidence to support global warming. What we have here is data that's been taken since the late 1950s showing the concentration of carbon dioxide on the top of an extinct volcano, Mauna Loa, which is located in Hawaii. And you see that in those intervening years it's gone from about roughly 310 parts per million, and currently it's about 380 parts per million. So that's a fairly dramatic growth. And if we plot the average temperature of the Earth, which is shown in the jagged lines, and the rising CO2 concentration, you see that there's a very strong correlation between those two. And people that model the climate show that somewhere between 2 and 5 degrees Celsius is the projected warming at the end of this century. Now, to give you some idea of what a 5 degree Celsius temperature change means, 5 degrees Celsius colder is an ice age, and we may experience as much as 5 degrees Celsius warming at the end of this century. So that puts a severe restriction on our ability to use fossil fuels. Okay, well, how much energy does the average American consume? It's essentially 11.2 kilowatts of heat. And I recognize that not everybody can relate to that unit very well. So let me put it in terms that everybody can relate to. It's essentially 6 hair dryers worth of heat being released continuously, 24 hours a day, 365 days per year. So on behalf of every American, there's the equivalent of 6 hair dryers worth of heat being released somewhere in our economy. For example, at the local power plant, they're burning fuel to make electricity for us. Well, how much electrical energy, for example, or power does the average American consume? In the terms of work, that's about 2.24 kilowatts. And expressed in a way that we can all understand it, that's equivalent to 3 horsepower. So on behalf of every American, 24 hours a day, there's the equivalent of 3 horses generating electricity for us, driving our automobiles, providing air conditioning for our buildings, and so forth. Now imagine if we really tried to generate that power with horses. Horses cannot work 24 hours a day, so maybe we'd have to have 3 teams of horses, so that means about 9 horses per person. So we have about, 300 million people, so that's going to be close to roughly 3 billion horses we'd have to have in this country in order to supply the power. So it's a good thing that we've come up with other ways to make power for us. Okay, so I'm going to get now to the heart of my presentation, which is biofuels is one of the topics. In a conventional oil refinery, currently I mentioned the price of oil is about $70 a barrel. And what we do is we convert that crude oil into fuels, chemicals, and polymers. And currently the price of oil at the refinery gate, or the price of gasoline, is about $2.06 a gallon, which is about $87 a barrel. So in the terms of the oil industry, the so-called crack spread, the difference in price between the refined product and the raw material is about $17 a barrel, which is a little bit high. It's normally around $10 a barrel. Okay, if we were to use biomass as a feedstock, you can get lots and lots of biomass at $60 a ton, and on an energy basis, that's equivalent to oil at $20 a barrel. So in this case, using biomass as your energy source, the crack spread is about $67 a barrel, so which is much larger, so there's a greater opportunity to make a profit. The challenge is, what is the process that goes into that circle? There are many answers to that question. The one that I'm pursuing is called the Mixalco process. And let me introduce you to it. What we do is we take biomass and treat it with lime to make it digestible. Then we take that lime-treated biomass and ferment it into carboxylate salts. We remove the water from that salty solution and heat the salts to make ketones. And if we add hydrogen to those ketones, we get alcohols. Now let me express this in terms that everybody can understand. I imagine that you've heard of alchemists. Their goal was to convert lead into gold. And in a sense, what I'm doing is converting a worthless product, a manure in this case, into things that people want. So imagine we have manure going into our process. I'm going to convert it into the salt of vinegar, nail polish remover, and rubbing alcohol. So I can take something that people don't want and convert it into things that people do want. Now, what are the advantages of our technology? First of all, we can use wet feedstocks. The advantage of that is when you harvest your biomass, you simply go into the field one time, chop the biomass, and put it into piles, and these piles can be stored for as much as a year without significant degradation. So it's a very inexpensive way of collecting and storing the biomass, provided that it's wet. If you have to dry it, then you have to worry about, is it going to rain during the harvest season, and when I stack up my bales, is it going to rain on them and damage the biomass? We can also use a wide range of feedstocks, and what I'm showing here in this picture is the variety of different feedstocks that can go into our process. I'm going to highlight just a few of them. For example, we can use agricultural residues, and this photograph shows a pile of bagasse, which is the residue from sugarcane processing. Notice on the top of the pile are people, and so we're estimating the height of that pile to be 100 feet. So in fact, you can have these giant piles of biomass collected in a single location. We can also use energy crops, and what I'm showing here are 3 crops that could be used for energy: corn, sorghum, and energy cane. On the y-axis, I'm showing the productivity, that is how many dry tons per acre per year are produced. So let's talk about corn for a while, which is used to make ethanol fuel. This picture kind of shows the idea. We take the energy of the corn and put it into our automobile so that we can drive. I pulled this photograph off the internet of Bart and Philip. Philip is holding an ear of corn, and the reason I like this photograph is in the background you see the corn stalks that it took to grow that ear of corn. So there's lots and lots of biomass in the background, but all we're using is the ear, in fact just the grain of the corn. So hardly just a portion of the biomass that's grown is actually used in the process. We also have, what I'm showing here is the total amount of land that would be required if we wanted to grow all of our gasoline needs. That green square is the amount of land that would have to be planted in corn to grow all of our liquid fuel needs for gasoline. Plus we have this horrible problem where the corn is competing with food. So although this is a cartoon and meant to be funny, actually I find it to be quite sad. So now let's talk about sorghum. Sorghum is being researched at Texas A&M University, and what I'm showing here is a photograph of sorghum taken in November. It was planted by seed in April, so from April to November it grew about 15 feet high, and you can see Cesar Granda standing in the front there as a model to give you an idea of how tall this is. So it's a very prolific crop, and it grows widely throughout the United States. Also, energy cane is a crop that can be grown. Here we see a photograph from Puerto Rico. There are 2 men standing in the bottom left-hand corner, and you see next to them is 1 year's growth of energy cane. And in this photograph you see it harvested, and you get a sense of how tall it is when it's cut. We can also use garbage as a feedstock. This photograph gives you the idea. It reminds me of Back to the Future 2, where they were taking garbage and putting it into the Mr. Fusion machine to recharge the flux capacitor in the DeLorean time machine. Well, I could never get the flux capacitor to work, so I'm using my technology to convert the energy of garbage into fuel. We're also very energy efficient. We don't use genetically modified organisms. We use what nature provides. There are many, many products that we can make from our process. And we use something called distributed processing. And this image shows what I'm trying to explain here. Each of those dotted circles represents a farm, and there's a truck on the farm that takes the biomass and brings it to that center circle, which is essentially a pile of the biomass, which is our fermentation. So as the biomass is being fermented, it makes the salty solution, the carboxylate salts, and then we pipe that salty solution to the central facility, which is shown as a square box at the very middle. And what we do is we process and upgrade that salty solution, ultimately making something such as ketones that go through that black solid line, which is essentially a pipeline. We get to the local waterway where there are barges that take the liquids to the refinery. We upgrade those liquids into gasoline and ship it through the existing pipelines to deliver it to the local gas stations using our existing infrastructure. Okay, another important advantage of our technology is it does not require enzymes and it does not require sterility. Both of these greatly lower the cost. Speaking of cost, what is the economics of our process? Let's use one example of garbage as a feedstock. What I'm showing here is the return on investment on the y-axis for making alcohols or gasoline using our technology. So at $70 a barrel, which is the current price of oil, alcohol sells for about $2 a gallon, and we can make about a 50% return on investment. And gasoline sells for just a little over $2 a gallon. We'd make 25% on our investment. Let's talk about return on investment. What does that mean? Imagine that I have $100 and I give it to the bank. At the end of the year, I can take my $100 out of the bank and they might give me $3 or $4 as interest on the loan that I made to them of my $100. In the case of our process, if you invest $100 into our process, at the end of the year you'd get your $100 back, but you would get $50 back as your profit for having invested in that process. So it's a very profitable venture to turn biomass into liquid fuels. Now the reason alcohol is more profitable than gasoline is alcohol enjoys a subsidy from the federal government, but if there's also a subsidy available for biogasoline, so if we collect that subsidy, we'd make about a 55% return on investment. So both of these are very attractive scenarios. What about growing our biomass using energy plantations? The return on investment is very similar. In the case of alcohol, it's about a 55% return on investment. In the case of gasoline, about a 15% return on investment. And if we have the subsidy for the biogasoline, again, it's about a 55%. So it's a very profitable thing to do when oil is $70 a barrel. Okay, a little history about our technology. In 1991, we started developing this process in the laboratory. And in the year 2000, we started constructing a pilot plant, which is shown in this photograph. And in the year 2008, just last year, we started building a demonstration plant. And here you see the first engineering drawing. Basically, it's a pit dug in the ground, and there's a cover on top of it. To give you a sense of the scale, it's about 50 feet high at the middle and about 100 feet wide at the base. And here you see the hole being dug in the ground for the pit. And then we're lining that pit with concrete, more concrete, more concrete. And then these are the tanks that stand next to the pit that we use to collect the fermentation broth. And here you see the total of 4 tanks standing next to the pit. And then finally we've covered the pit with a tent-like structure. Now the technology is very analogous to the rumen of a cow. The organisms that are digesting the biomass and converting into the carboxylate salts are the same kind of organisms you find in the rumen or the stomach of a cow. So to help make that point, we did some photoshopping and put the spots onto the cover to show that it's essentially like a cow. So what we're trying to do is develop a giant cow that digests biomass and turns it into carboxylate salts. Here you see the interior of the fermenter, and notice at the back of it you see 3 holes. That's the sump where the liquid is collected, and on the sides you see gratings that allow liquid that purges through the biomass to be collected. So the idea is the liquid drains through the biomass and collects in the sump. Next, what you see is us loading 300 tons of biomass into the fermenter. The biomass comes with a front-end loader, and then there's a kind of fire hose with a mixture of water and lime, and the idea is that water and lime and biomass are all blended together, and they then sit in the sump, and they're there for about a month roughly. We blow air up through the pile, through those gratings that you saw on the previous slide, and the combination of air, lime, and water takes out lignin, which is the glue that holds the biomass together, and it hence makes the biomass very digestible. We had a dedication in November of 2008 of our facility, and we were very fortunate. The governor of Texas was there to help us dedicate the facility, and they allowed me to have a few words to say as well. And the gentlemen that are shown here are the people that funded this plant, and they name it Energy Independence 1. My family had a chance to pose with Governor. And this next slide shows Governor Perry and myself and my son, who's the gentleman in the lower right-hand corner. And what I love about this slide is my son is looking into the future. Next, what I'd like to do is talk about my engine research. And I'm going to start my story with a conventional automobile that gets about 30 miles per gallon on the highway. In this image, what I'd like you to imagine is going from New York to Los Angeles, and it takes about 93 gallons of gasoline to make that trip. The green block is the mound of land area that would have to be planted in sorghum to supply 100% of U.S. gasoline needs. It's a fair amount of area, and it would be nice if we could reduce that. So the question is, can we come up with better engines that would reduce the amount of land necessary to supply our gasoline needs? What I'm showing here is the star rotor engine, which is the engine that I'm working on that I think will increase our efficiency dramatically. It uses the same thermodynamic cycle as a jet engine. So if you've ever flown in an airplane and noticed those engines that are hanging on the pods under the wings, we're trying to put a jet engine into everybody's automobile. The way the engine works is it has a compressor, which is shown in the left, and an expander, which is shown at the right. We have air coming in. It's compressed using the compressor. The air coming out of the compressor goes into a heat exchanger where we capture waste heat coming off of the engine. Then in the combustor we add fuel. The fuel burns and makes the air even hotter. So coming into the expander, what we have is very hot, high pressure air. That air expands in the expander, and it does work. So the work that's produced by the engine actually comes from the expander. The hot gases coming out of the expander are at 1 atmosphere of pressure. We take those hot gases, go into the heat exchanger, capture that waste heat by recycling it back into the engine, and send off into the world a relatively cool exhaust. Now, we've not yet built the complete engine, but we have built the compressor, and we've measured 82% efficiency in the compressor. And when you go through thermodynamic analysis, you can calculate that the engine efficiency would be between 57 and 66%. And to put that into context, a conventional automobile engine is about 20% efficient. So what we're saying is that this engine would be about 3 times more efficient than a conventional engine. So this is how it packages. It's on a common shaft, both the compressor and the expander. And then you can see at the top is the heat exchanger, and that orange box is a representation of the combustor. So if we take a star rotor engine and put it into a conventional automobile, we would get about 3 times the fuel economy. So now we're talking about roughly 90 miles per gallon, and our cross-country trip from New York to Los Angeles would take about 31 gallons of gasoline. And you see that the land area shrinks by a factor of 3. Well, can we do better than this? And the answer is yes, we can. If you package the star rotor engine with a Loremo, which is a high efficiency automobile body, it has a low drag coefficient and very low rolling resistance tires. In that package, we get about 235 miles per gallon. And now our cross-country trip from New York to Los Angeles takes only about 12 gallons of gasoline. And if everybody were willing to drive Loremos, you see that the land area shrinks quite dramatically. Well, is that the limit of technology? No, we can do even better. Excuse me. If we package the star rotor engine into an Aptera, which is an automobile being developed in California, you see that we get about 380 miles per gallon. And now our cross-country trip would take only about 8 gallons of gasoline. And the land area required to supply all of U.S. gasoline needs, if everybody drove Apteras, shrinks to be quite small. If you like the Aptera, here you see some shots of it. Notice at the left there's a solar panel on the roof. It is a hybrid vehicle, so when it sits in the sun, you're actually charging the battery, so you can partially drive your automobile on solar energy. And this is what it looks like on the inside, and since it's available in California, every Aptera comes with the view that you see out there. This is my final slide, and it shows the grand vision. Notice on the left we have the crops, perhaps sorghum, that are growing. We take those crops, we put them into the biomass processing facility, and coming out of that facility we have either ketones or acids. Those are brought to the nearest oil refinery. There we take fossil fuels such as natural gas and reform them into hydrogen and carbon dioxide. That carbon dioxide is available at a central facility, so what we can do is pump that CO2 under the ground and sequester it so it does not get into the atmosphere. The hydrogen is attached catalytically to the biomolecule, goes into the oil refinery, and comes out as alcohol or gasoline. Those products can go into existing pipelines and existing gas stations and existing automobiles. Now, sure enough, when you burn that fuel, coming out of the tailpipe is carbon dioxide, which goes into the atmosphere, but through the process of photosynthesis, that carbon dioxide is fixed as new plant matter, and so what we have now is a cycle with the carbon going around and around in the loop. In fact, we can use some fossil fuels to hydrogenate these biomolecules, but the carbon dioxide from the fossil fuels is sequestered underneath the ground. Now, ultimately, the objective is not to use a conventional automobile at the right, but to use a hybrid vehicle with a star rotor engine in it. So that means that we need less land area in order to grow the crops that we need to supply our fleet. Well, thank you very much for your attention. I hope that you enjoyed this presentation. I also wish you good luck with your life and your future career.